So today what we want to look at is a little bit of a closer look at one-sided limits. We addressed this briefly earlier, but I want to kind of focus in on this note that we mentioned before, and that is, when does a limit exist, okay? By the way, if you're told to show that a limit exists on a particular problem, you need to actually go through these steps, okay? You need to show that the left-hand limit exists and tell what it equals. You need to go and show that the right-hand limit exists and tell what it equals. And then, therefore, because the left-hand limit equals the right-hand limit, the limit exists, okay? So that's one way that you can prove that the limit exists. All right. So let's talk about this real quickly here using a couple of examples. Remember the notation. If it has a little negative after what x is approaching, that is approaching from the left. A plus sign means it's approaching from the right. If you forget, just think about your x-axis. Okay? So as we look at this function here, as this is asking us to find the limit as x approaches 0 from the right of the hyperbola 1 over x. Okay, so what is it approaching as we approach 0 from the right? It's going towards infinity, right? It's going towards positive infinity. So what would we say the limit is as x approaches 0 from the right? We would say it does not exist because it's unbounded. Okay?
So
all right.
You never want us to say infinity as a limit?
No. In general, we'll just say that the limit does not exist because it's unbounded behavior.
So
Okay?
explain it too.
You can. That would help. One of the great things is that you can get. That you need to learn how to do better is just to get used to explaining yourself. When you do this big long problem or something, make sure you state your answer very clearly. If you're told to prove something, don't just show the work to prove it. Make sure you give the therefore, this is true because of this. Don't expect the reader to draw the conclusions for themselves. You need to communicate those conclusions, all right? In this case, it's approaching a positive infinity, therefore we say the limit does not exist. Okay? How about this one? We have a semicircle. A semicircle. The limit of f of x as x approaches negative 2 from the right. Okay? So we're taking the limit as x approaches negative 2 from the right of 4 minus x squared. What's that going to be?
You can just plug it in and you get 0.
Okay, if we plug it in, coming from the right, we get 0. Okay? Now let's take this example one step further. What would the limit as x approaches negative 2 from the left equal?
Does not exist. Does not exist.
Well, why not? Can't we just plug in negative 2 and get 0?
Like it would be like a negative under the. There's nothing on the radical. So it doesn't exist.
Okay, if we plugged in anything to the left, we'd get a negative under the radical, so it'd be imaginary. There is nothing on the graph, you observe there. So we can't approach from the left. There's nothing to approach from. All right? And this is a good example of one of the cases where a limit will not exist is at an endpoint. Okay? Watch for endpoints. All right? Watch endpoints. Well, notice here, okay, the right-hand limit does exist, it equals 0. The left-hand limit does not exist, because there's nothing to the left. So, taking this another step here, what would we say about the limit as x approaches negative 2 of 4 minus x squared?
The end.
Does not exist.
Does not exist, okay? Both sides have to exist and have to be equal, okay? So here's the case if they said show whether or not, don't just say, oh, it's an endpoint. You know, show why not. Show that the left-hand limit does not exist, therefore the limit doesn't exist. Okay? Nothing too difficult there. Let's take a look at kind of an odd looking function. This you actually can do on the calculator. This is the greatest integer function. Okay? Or you might have heard this called a step function. Alright? So basically what it is, it's kind of hard to tell this on the calculator, but you can see it's defined as the greatest integer n such that n is less than or equal to x. Okay? So, n has to be the integer, and it's less than or equal to x. So when n equals x, that's when we have a point, like there, n equals 1. Alright? So n would equal 1, and x would equal 1. Alright? But then, as x gets bigger, n is the smaller integer. So x is continuing to get bigger until it gets to 2. Then it jumps up. Okay? So you see that you have these strings, or these stair steps, so you could visualize it as, where you have a closed point on the left and an open point on the right. Okay? And that's how all those are. Your calculator does not do open points and closed points, alright? But that's what's there. Okay? Now you'll notice here on the calculator I have the function shown, it's int x. Alright, that is under math, go to number, and 5. Okay? Yes?
If it's less than or equal to, shouldn't that, like, why is it a hole on the right if it's less than or equal to?
The integer is less than or equal to x. Okay? So at 1, 1, the integer is equal to x. As soon as x gets to 2, then n can be 2. Okay?
So at 1 it doesn't exist, but at 2 it does.
Yeah.
Okay.
Because it has
Yeah, there's a point, there's a jump there. Now we're at 2, 2, and then 3, 3, 4, 4. Yes?
Does that mean the integer can't be anything other than that first spot? Because that's the only spot where it's less than or equal to x. Like all the way on the left. On the little staircase thing here.
Yeah.
It can only equal that point. It can't equal anything else because it's more.
Yeah, right here from x equals 1 up until you get to x equals 2, the y value, which is our n, will always equal 1 in here.
Okay.
But then as soon as you hit 2, it jumps up to 2.
Okay.
And then it's 2 all the way up until you get to 3, then it jumps up to 3. Okay? Alright, so the limit as x approaches 0 from the left. Limit as x approaches 0 from the left of this greatest integer function. It's just kind of a double bracket. What would that equal? Yeah, -1, okay? It's approaching -1. Does it actually equal -1? No. But it's approaching from the left -1. Okay? The limit as x approaches 0 from the right would equal, who said it? 0. Okay? We are approaching 0 from the right. Okay? So what do we know about the limit of this function as x approaches 0? It doesn't exist. Yeah. If I say just the limit as x approaches 0, that will not exist because the left and right hand limits are not equal. Okay? Alright, taking our time on this, but I want you to get used to the notation. I want you to get used to thinking of that idea of approaching. Alright? So, now we want to consider something called continuity. Alright, continuity. And I want to introduce the idea here with some examples first before we actually come up with a definition. Okay? It says determine the limit and discuss the continuity. So I've created a little table here for you. So we have this function here, and c is -2. So we're approaching this value -2, and it says that the point is -2, -2. So as x approaches c from the right, what's our limit? It's -2. As x is approaching c from the left, what's our limit? -2. So, what is the limit as x approaches c? -2. Alright, good. Now, question. Is it continuous here? Yes, okay. Think back to kind of the old definition of continuous, the real simple definition, and that is just any function you can draw without lifting up your pencil. Okay? That's kind of like the elementary school definition of continuous, alright? And it's a good one. So it is continuous there. We're going to look at a rule later on, though, to explain why just by looking at our limits. Okay? Alright, how about number 4? Here again we're approaching -2, and you can see here this function has an open point at -2, 2, and the function is defined at -2, 3. Okay? So what's our limit as x approaches c from the right? It's 2. Okay? How about as we approach from the left? 2. So what's the limit as x approaches c? It's 2. Is this continuous? No. So, hang on, what conclusion can we make based on these two examples about limits and continuity?
As long as it's continuous leading up to the point, it should be fine.
Okay.
If it's the same approaching from the negative and positive,
Then what?
then it has the same limit.
It'll have the same limit, okay.
If it's like the limit doesn't equal the actual function at that point, then it's not continuous.
Okay, there's the connection between the limits and continuity, and we'll look at the formal definition of this later, but right here you can see that the fact that the limit equals something and the limit exists does not automatically imply that the function is continuous there. Okay, because both of these have a limit that exists, but the function is not continuous in the second one. And what Austin said is actually exactly right, and that's going to be our definition we'll look at later. If the limit equals the value of the function, then it's continuous. Okay? So if the limit as x approaches c equals f of c, then it's continuous. So here f of c was -2. That's the same as our limit. It's continuous. Here, what's f of c? It's 3. But the limit equals 2. Therefore, there's a discontinuity there. Okay? Good, good. All right. This number 6 here is x. C is -1. So as we approach from the right, what's our function approaching? 0. And as we approach -1 from the left, 2. So what's our limit?
Doesn't exist.
Does not exist. Is this continuous? No. So can we make any other kind of a statement about continuity?
If there's no limit, then it's not continuous.
Yeah, if the limit does not exist, it's not going to be continuous. Think about it the other way. If we know a function is continuous, what do we know about the limit? There is going to be a limit. Okay? So, that's those are some of the conclusions we want to draw here. All right? Now, let's think about this one here. The limit as x approaches 2 of the absolute value of x minus 2 over x minus 2. Someone tell me what this might look like. Can we graph it?
It'll
A V with
change at 0, like change slope at 0.
At 0?
Oh wait, no, I see a V range.
So wouldn't there be a V and then like a straight line?
Isn't it just like a line that's like this, but over 2 to the right?
Okay, that's good. All right. What's x minus 2 over x minus 2 equal? 0, as long as, or not 0, 1, got me. 1, anything divided by itself is 1, right? So as long as x minus 2 is positive, you're going to have positive over positive, right? So that's going to be a positive 1. Where is going to be that point where it's going to switch from being a positive to my numerator is positive always, but my denominator is now negative? Where's that going to take place? At 2. At 2. Okay? Now we know that this is not defined at 2 at all because we'd be dividing, alright, by 0. But check out what happens. When x is bigger than 2, I've got a positive divided by a positive. That's going to be 1. So we've got this. When x is smaller than 2, we're going to have the absolute value of a negative, which is positive, divided by a negative, which will be negative. So that's going to end up being -1. Notice I have an open point on both of these because x is not allowed to equal 2. Okay? So, now that we know what it looks like, what is our limit as x approaches 2 from the right? 1. It equals 1. Because we are actually approaching 1 as we come from the right. All right, one more here. take a minute here and try to sketch this piecewise function on your own. We have it? I've got the screen frozen. But alright, let's take a look, see how you did. Alright, it should look something like the solid parts of that. The dotted parts are the parts of those two lines that got cut off. But less than or equal to 1, I'm on that line y equals x. Okay? Once I get past x equals 1, I jump down to this line, 1 minus x. Okay? If you want to leave the dotted portions there, you can. If you want to erase them after you get done, that's fine too, but or if you just want to use a different color and highlight the part that you want, that's fine too. Just make sure it's clear. Okay? So now, what is the limit as x approaches 1 from the right? It's 0. Okay? This is 0. Alright. So, that's just a couple of examples here to illustrate the idea of finding limits on one side or the other, and also this concept of continuity. So, let's talk about when does a limit exist and continuity. Alright, so here's kind of a formal presentation of the definition we already looked at, or the existence of a limit that we already looked at. If f is a function, and let c and L be real numbers, the limit of f of x as x approaches c is L if and only if. That means both of these have to be the same. And also it means that if these are correct, then the limit will approach L. So that's the if and only if. It means it works both ways. It's a biconditional. Alright? But what has to happen is the limit as x approaches c from the left of f of x has to be L, and the limit as x approaches c from the right of f of x has to be L. Okay? So now, continuity. Continuity. A function is f is continuous on a closed interval AB. Notice the closed interval. If it is continuous on the open interval AB, and the limit as x approaches a from the right is f of a, and the limit as x approaches b from the left is f of b. In other words, the limits are approaching the actual endpoints here. Okay? Or the limits are the values of the endpoints on either side of the interval. Okay? Now, there's this concept of continuous from the right and continuous from the left. When we're talking about endpoints, kind of like that semicircle we saw earlier, okay, we can say that it is continuous from one side or the other. Okay, so just to illustrate here, we have this function, and a is on the left. It is continuous coming from the right to this left endpoint. Okay, now obviously we wouldn't say it's continuous through a because there's nothing on the other side. Okay, but we can say it's continuous from the right at a. And then same thing with b on the right hand side, it's going to be continuous from the left at b. Okay? So a little bit of a distinction here, but that's continuity on a closed interval. Okay? So here, discussing the continuity of this semicircle, square root of 1 minus x squared, what would we say about the continuity of f of x here?
Continues from the right at A and continues from the left at, well, at F1.
So it's continuous from the right where?
At -1.
Okay. Okay. And what else?
Continues from the left at 1.
From the left at 1. What else can we say?
It's continuous from -1 to 1.
Okay, it's continuous. Not and. On. We would say the open interval from -1 to 1. Okay, it's defined for everything between -1 and 1. So as a result, we could say therefore, it is continuous on the closed interval. Just using that definition we saw above. It's continuous on the closed interval from -1 to 1. Okay? It's continuous from the right at -1. That means f of -1 equals the limit as we approach -1 from the right. It's continuous from the left at x equals 1. That means f of 1 is 0, and the limit as x approaches 1 from the left is also 0. Okay? And then because it's continuous on the open interval, now we can say it's continuous on the closed interval. Okay? All right. Now we could make, just for sake of time, I'm not going to go through these. We could come up with similar definitions to cover continuity on a half open interval. Okay? Or even on infinite intervals. If it's closed on one side or limited on one side but not on the other, we could say that. Okay? For sake of time, I'm not going to develop that any further. Here's where it gets a little practical, okay? And that is continuity. Remember we said when we were starting to do limits that you can just plug in the value at x is approaching if you know the function is continuous around that value, okay? So like that's why we said, you know, all quadratics are defined for all real numbers. We know they're continuous everywhere, so we can just, if we're taking the limit of a quadratic, we can just plug it in. Alright? Well, here's kind of officially why. Alright? A couple of things here. B is a real number and f and g are continuous at x equals c. Then the following functions are also continuous at c. Alright? If we multiply the function by a constant. Alright? So if you have a quadratic and you multiply it, so now it's 7x squared. That doesn't change anything with our continuity. Alright? The sum and the difference. If you have two continuous functions and you're adding them or subtracting them, that's if also going to be continuous. Likewise, multiplication. If we have two continuous functions multiplied together, we can know that that product is also going to be continuous. And then the quotient, or division, if we have f divided by g, as long as g does not equal 0 at that point, it's going to be continuous as well. Okay? So that's where we ran into trouble with sine x over x. Those are both continuous at 0, but x equaled 0 at 0. So there we had an issue. There's not continuous there, but we were able to find a limit. Now, couple other couple of things here, and make sure you understand this. These four types of functions are continuous for every point in their domains. Okay? polynomial functions. So, not just quadratics, but cubics, quartics, quintics, any polynomial function. Rational functions, as long as the denominator does not equal 0. Okay? Radical functions. By the way, remember, by definition, rational functions were made up of two polynomial functions. We use that term a little bit looser than the actual definition, but rational function, if you have two polynomials divided, you know it's going to be continuous. The radical functions, all right? And notice here the index doesn't have to just be a square root. It could be a cube root, fourth root, whatever. Again, at every point on their domains. And then also the trig functions, sine, cosine, tangent, cotangent, secant, cosecant. Obviously 4 of those have asymptotes. So those are discontinuities, but those aren't in the domain. Every other value in the domain we can say it's continuous at. Alright? So as a result, just to see kind of the conclusion here, you know, x and sine are both continuous, so x plus sine is continuous. 3 times tangent is going to be continuous everywhere tangent's going to be continuous. X squared plus 1 is continuous everywhere. Cosine is continuous everywhere. So if I divide them, this is going to be continuous everywhere that cosine doesn't equal 0. Okay? Alright, so now bringing in another thing that we looked at before, but with a new application. We said that the limit exists on a composite function. We could find the limit of the inside and then just evaluate that in the outer function. Well, here we're talking about continuity of a composite function. If g is continuous at c and f is continuous at g of c, notice it's not f is continuous at c, it's f is continuous at g of c, then the composite function given by f of g of x is continuous at c. Okay, by the way, for some reason we always still have people who get confused by this notation. Some call it the fog notation, alright? That little open circle is not multiplication, that's function composition. Okay. So, we can look at these and determine where they are continuous. So for A, tangent of x. Where is tangent of x continuous? On its domain, okay? So what is the domain of tangent? Okay. X cannot equal pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2. Okay? Now this says describe the intervals, so let's try to actually give an interval, some intervals. It would be an open interval, right? An open interval from negative pi over 2 to pi over 2. And then, or from, pi over 2 to 3 pi over 2, etc. that direction. Let's do that better. There we go. From negative pi over 2 down to negative 3 pi over 2. And we could keep going that direction as well. Okay? You could also state this, each of those is pi apart, right? So you could state it as pi over 2 plus n pi, and n has to be an integer. Okay. And then you could just say it's continuous on the interval negative pi over 2 plus n pi to pi over 2 plus n pi. Okay? And that'll give you all of those infinitely in both directions. Yeah.
So the question is, describe the interval in which each function is continuous, and we said that the domain of the tan function can equal pi over 2, negative pi over 2, all those things. So wouldn't it just be all real numbers instead of pi over 2, negative pi over 2?
You can. You could say all real numbers such that x does not equal pi over 2, and so on. Or the blue is kind of the general, covers everything. Okay. Here you're assuming the reader's going to keep going with the pattern. Alright? The blue actually states the whole thing. Okay?
Oh.
I'm just giving you some options there. Okay? Alright, how about this piecewise function? Sine of 1 over x when x is not 0, and 0 when x is 0.
Domain of sine is negative 2 pi to 2 pi?
No. What's the domain of sine? All real numbers. Often we would only give answers from negative 2 pi to 2 pi, but the actual domain is all real numbers. So the question, how can we tell if this is continuous?
Well, if there's a limit in sine that leads to 0.
Okay. The limit of g of x has to equal g of 0. That's the key point. We know everywhere else on sine of 1 over x is going to be defined. It's going to be continuous. The question is this the case? Okay. So when x is approaching 0, it's on sine of 1 over x. So what did we say about sine of 1 over x? What's the limit of that? It doesn't exist. Remember, that was an oscillating one, right? So therefore, we would say, nope. So what would the intervals be? Huh? So we know it's not continuous where? No, we said when it's sine of 1 over x, it's always continuous. We just had to figure out that right at 0, right? And what did we just show? That it's not, okay? So what are the intervals where this is continuous?
Everything except 0.
Everything except 0, okay? So the intervals, negative infinity to 0, open interval, or from 0 to positive infinity. Okay? that's what it would be continuous on. Okay. Last one here. Kind of similar to the previous one. Yeah, what's the limit? We already kind of know what we need to test. What's the limit as x approaches 0 of x times sine of 1 over x? Does this oscillate too? Should we check it? Let's check the calculator here. Let's see what this looks like. So x sine of 1 over x All right, let's check this out here. Okay, that's what it looks like. Is that oscillating behavior?
Yeah.
Let's see here. Let's zoom in a little more.
Oh, yeah.
Is that oscillating behavior? Yeah, this actually was one of the homework ones. X times the sine of 1 over x. This was actually from the homework on the squeeze theorem, or actually lesson 3. Okay? Oscillating behavior has to be bouncing back and forth between two fixed values. This isn't happening there. It's toning down to 0. Okay? It's zooming down into 0. So, the limit as x approaches 0 of x times sine of 1 over x equals 0. What is h of 0? 0. So, where is this continuous? All real numbers. Okay? This is continuous for all real numbers. Okay? So you got to be careful with those. Be careful with those with the oscillating behavior. That's why we gave you a couple of those to test with the calculator the other night. Okay? All right. So those are some properties, some different testing for continuity and whatnot. You have some practice to do with these, okay? When it's asking you to discuss continuity, make sure you're clearly communicating. If it's asking you to tell whether or not the limit exists or whether or not it is continuous, use those definitions, okay? Don't just say, because it looks like it, or don't just draw a picture, all right? Make sure that you use words to explain, okay?